So what can we do with Maxwell's equations? Well, we say that they contain essentially everything that we want to know about electromagnetic phenomena. Okay, so what about, I don't know. What about charge conservation? That's something we had discussed. We had a very important equation related to this, which was essentially the continuity equation. So where does that come from? Well, fine. So Maxwell's equations, the source of all truth. What are we going to do? Well, okay, I can do whatever I want with those. I'm going to take the Ampère-Maxwell equation and, just for fun, I'm going to take its divergence. Right? So what do I have? I have Ampère-Maxwell, Amp-Max. Okay, it tells us that the curl of B is equal to mu0 J, current density, plus mu0 epsilon 0 dE dt. That's great. I take the divergence. So on the left-hand side, I have div of curl of B. On the right-hand side, I can factor out a mu0, and then I'm going to have div of J plus some epsilon 0, and then okay, fine, ddt, the ddt is going to commute with the divergence because they're different variables, so I can write this as d dt div of E. Okay, mu0 factored out. Well, so by construction, this thing is 0. The divergence of a curl is always 0, just a mathematical fact, non-negotiable. On the other hand, we also have that Gauss's law tells us that the div of E is equal to the charge density rho over epsilon 0. Okay? So what does that tell us? It just tells us that, you see, ddt of rho plus div J is equal to 0, which was our continuity equation from before. Okay? So charge conservation at a local level is an inbuilt feature, an inbuilt consequence of the Maxwell equations. We just needed Ampère-Maxwell, and we just used also Gauss's law. That's it. Okay, so this is the kind of magic that you can do with these things. I guess I'm not quite sure how much of this stuff you've seen before, but this is just like simple magic that you get from this. Before, we essentially used the tautological reasoning where we said, oh, let's just assume the local conservation of charge and derive the continuity equation from that. Now the viewpoint has changed. We believe in the Maxwell equations, and the Maxwell equations do tell us that this is what occurs here. Okay? Now, just a little note for the mathematicians among you. You could say, well, fine, but let me then come back to my Maxwell equations and, my charge density and my currents. These are things that I can put as input. I mean, I come to my lab and I just put these things to whatever I want. And then they're sources for the electromagnetic fields that I have. So what if I'm a brilliant experimentalist and I'm able to construct a charge distribution that is time dependent and a current distribution also that is, space and time dependent, and that don't fulfill the continuity equation? What happens then? Okay? So actually what happens is that you can never do that. You'll never be able to do that, because then you would be creating charge or annihilating charge out of nothing, and that would be a very interesting phenomenon. Okay, so essentially the experimental fact that we had at the very beginning, that we mentioned that charge is conserved, is an input globally in the whole theory of electromagnetism that is just manifested at this level, but it is an input, it is an experimental fact. Okay, in the end, Maxwell's equations are based on countless experiments that have been done with these fields. Okay? So that's the idea. So that's about charge. Then, well, what other things can we think of? So charge essentially is measured locally by the charge density. It flows with a current, which is very easy to visualize. You just see charges moving around with certain velocities, and that's your current. However, of course, there are other quantities of interest in the theory of electromagnetism. For example, energy. And we've discussed that a little